So the last subject that we'll be covering in this introduction to M-array modulation is the difference between bit error rate probability and symbol error rate probability. So this, in the case of binary, a symbol is a bit, and so there's no ambiguity, but as we go into M-array signaling, we have these two possibilities. And sort of glossed over it so far, but now I'd like to throw a spotlight on it and draw your attention to the difference and find the relationship between the symbol and the bit error. So symbol error probability is what we've discussed so far. Remember, we talked about points in the constellation, about the minimum distance between points in the constellation. These were always symbols. And so we were always calculating with the union bound, what is the probability that I'm going to make an error between this symbol and that symbol? So we called it PE, probability of error, to avoid this discussion too early about bit versus symbol to not be too confusing. But I think now it's important to appreciate the difference so that we can see that our equations are for symbol error rate, whereas when we're plotting in MATLAB BERT tools, for instance, it's in the bit error rate, and to be able to see where these two come together. So if we want to be able to determine what the bit error rate probability, we have to consider how bit errors occur in M-array signaling. So it's going to be different for orthogonal modulation and non-orthogonal modulation. That's the first thing. And let's start with the easier case, I think, of orthogonal modulation. So orthogonal modulation has equidistant symbols. I'm assuming that they all have equal power. They're orthogonal and equal power, in which case they are equidistant, such as MFSK. And the idea is, remember that they're on the corners of these hypercubes in n-dimensional space. And let's call PS the probability of symbol error. Instead of calling it PE, let's spell it out for symbol error that it is. And we know, let's look at the probability of symbol error, for instance, for the probability that symbol 0 is received in error. Well, the probability that symbol 0 is received in error is just the sum over all possible ways we could make an error. So we can make an error by thinking it's S1 or S2 all the way up to S-1. So I would say it was the sum over all these probabilities. So what's nice in orthogonal modulation is that there's such symmetry in the modulation that all of these conditional probabilities are equal. The probability of mistaking symbol 0 for symbol 1 is the same as mistaking symbol 0 for symbol 5, all the same. So there are m-1 terms in the sum, so it ends up just being m-1 times, and I could use any one here, but I chose symbol 1 when symbol 0 is sent. Of course, if this was the probability of receiving 0 in error, if I wanted to do the average probability of symbol error, it would be averaging over all of them. But of course, that would just be 1 over m times the sum of m terms, so it comes out to be the same. So let's think about this. It's the orthogonality, and they're equidistant or equal power, that tells us that really there's only one probability that matters, and they're all the same by the symmetry. Because of these assumptions, they're all the same, and that's why this can be simplified. So let's just say that the probability to choose SI being received when SJ was actually sent, let's just solve for that, and that's the probability of symbol error divided by m-1, the simple relationship between these two quantities. And we're going to play with it in both directions. The probability of symbol error equal to this, and the conditional probability equal to this. So I said we have to figure out how bit errors occur. So let's think of a symbol. A symbol has a mapping to it. Each symbol has associated with it a vector of bits, a collection of log 2n bits, and this vector is assigned to a symbol. So let's look at the kth bit, some arbitrary bit in this sequence of length log 2n. One of the symbols is the correct symbol, and that means that all the other ones, m-1 symbols, are incorrect symbols. And among these m-1 symbols which are incorrect in their vector, how many of them happen to have the same bit in position k? So I think about, there's one symbol I'm looking at here, there's all the other symbols in the constellation, and all of these other symbols, I look at the vector of bits assigned to each one of these other symbols, and I start looking at the kth bit. So the kth bit here in this symbol is whatever, 0, 1, and I look for them all, and of course I can divide them up, and there's going to be m divided by 2 minus 1 that have the same bit in the position k. So m-1 are incorrect. M over 2 minus 1 have bk, which is good anyway, and the other m over 2, well, they have the wrong bk. They flipped that bit. Okay, so now I can take this probability of symbol error. Remember, probability of symbol error was m-1 times the conditional, m-1, but I'm going to divide that m-1 into the two groups. There's a group that is m over 2 minus 1, and another group that's m over 2. And of course, if I add these up, I'll get this relationship. But it's important because now I can identify that this m over 2 minus 1, they had no error in the kth bit. This part contributed an error in the kth bit. So I can concentrate on this red part. That's going to be contributing to my bit error. So now I just say, well, I'm going to use the relationship in the other form to be able to tell me not what's the relationship between the bit error, which is this quantity, and the conditional probability, but what's the difference between, what's the relationship between this bit error and the symbol error? So now I just substitute in again that same relationship. I put when I see the conditional probability, I put PS divided by -1. I get this result. And again, this part contributes to the probability of bit error. So that means that I can write this equation out now and say that the probability of bit error is just equal to m divided by 2 times the probability of simple error divided by m-1. Or we can put the PS over 2 here, and we have m divided by m-1. Now for large m, m divided by m-1 is almost 1. And so we can say that asymptotically, the probability of bit error becomes about the symbol error divided by 2, because roughly, half of the symbols have the same bit and the other half don't. So this quantifies for orthogonal modulation this relationship between symbol and bit probability. So what happens with the non-orthogonal modulation? Well, everything's a little different because for sure the symbols are not necessarily equidistant from each other. And because they're not equidistant, they're also probably, even if they were equal power, even if they were equidistant from the origin, like let's say PSK, the symbols are not equidistant from one another, even if they're equidistant with the origin, because there'll be some points which are close together on the circle, some points that are far apart. And of course in QAM, they are neither equidistant from the origin nor equidistant from each other. There'll be nearest neighbors which are close, far neighbors which are far. So that assumption that we had for orthogonal modulation simply does not hold in non-orthogonal modulation. So for sure the calculation is going to have to be different. We know that the error probability, the symbol error probability, is dominated by the nearest neighbors, by the symbols which are closest to one another. That's why we looked at d-min. So what we want to do is we don't want to be stupid. We do not want to do a bit mapping between bits and symbols such that when I have a symbol error, a whole bunch of bits go wrong, a whole bunch of bits go in error, because that will dominate our total average. It'll be dominated by these bad choices. So what we do is we're going to be smart in how we assign bits to symbols, and we call that smart choice a gray code. So a gray code will be a selection of the mapping from bits to symbols, which keeps the relationship, keeps the bit error rate as small as we can for a given symbol error rate. The symbol error rate is decided by the constellation geometry, and then that's fixed. But now I have probability of bit error, and I want to, whatever the probability of symbol error is, I want to keep that bit error as small as possible. And I think an example makes this clear. Let's look at 8 PSK. So we have 8 points along the unit circle here, and let's say that we assign to this angle, we assign 0, 0, 0. And look, like here, I'm counting in binary as I go around the circle. So I got 1, then 2, binary 3, binary 4, binary 5, binary 6, binary 7. So this is one way of allocating, giving the mapping from bits to symbol. Now, is this a good choice or a bad choice? This is a terrible choice. The opposite possibility would be to use a gray code, which is a good choice. And now let's try and see, if we can, what the difference is between these different assignments. Let's look at these two nearest neighbors. These angles, these points in the constellation are near one another, and so they're an error that could happen, one of the likelier errors of symbols. And we can see that when we make this symbol error, we're making 3-bit errors. 3-bit errors, like the maximum possible number of bits are going to be messed up. Now, if we look at the gray code of same symbols, we can see that there's only 1 bit that changes from here to here. We could say the Hamming distance between these is 1, whereas here the Hamming distance was 3. So the larger the Hamming distance, the more bit errors I have for a given symbol error. So we can see that this gray code has been a selection of the mapping so that every time we go between nearest neighbors, any nearest neighbors, the Hamming distance is just 1. There's only 1 bit that gets flipped. So if I make an error in symbol between nearest neighbors, and most of the symbol errors are going to occur between nearest neighbors, here I ensure that when this happens, only 1 bit is flipped, and that's called a gray code. So we're really just trying to avert disaster by making a choice, a good choice of mapping from bits to symbol. So you can have a gray code for QPSK. It's not hard to find that. And you can have a gray code for QPSK, 16 QAM. Now, as we get larger and larger, there are compromises that have to be made. There are not necessarily mappings available that have only a Hamming distance of 1. But of course, we'll try to keep the Hamming distance as small as possible to keep the probability of bit error as small as we can. So using gray coding, if we assume that we use a gray code, then it's easy to see that only 1 bit flips, which means that the probability of bit error would be the probability of symbol error, but divided by log 2m. For instance, in terms of 8 PSK, that would be 3. So it would be the probability of bit error be 1/3 the probability of symbol error, because on average only 1 of the 3 bits is flipped. And this is accurate, this approximation, as long as the symbol error rate is small, so that indeed most errors are occurring at the nearest neighbor.